Math 2414, improper integrals, infinite limits of integration. As we discussed in the previous video, there are two types of improper integrals. One where there's an infinity or negative infinity as a limit of integration, or possibly both, and the other where the interval over which we're integrating contains a value that is a discontinuity for our function. But let's talk about the types of integrals that have an infinite limit of integration. And there's three categories. Category number one, you're integrating a function from some constant to infinity. Category number two, you're integrating some function from negative infinity to a constant. Or category three, you're integrating some function over the entire real number line from negative infinity to infinity. The recurring theme that you'll notice in not only this type of improper integral, but the improper integrals that have a discontinuity somewhere over the interval of integration, is we identify the problem, we give it a nickname, a variable, and then we take a limit. But that's going to be the trick to all of these. And in the next video, I will review some of the common limits that we're going to run across. But right now, let's formulate a plan of attack. Let's take a look at this first type, integrating some function from a constant a all the way to infinity. To do this, we replace the problem with some variable. In this case, the problem is infinity. Now, I'm leaving a space in front of it because I'll be writing something there. We're going to replace the infinity with a t just for a second. And so we're integrating from a to t f of x dx. We figure out what that interval looks like if it had some constant limit of integration, upper limit of integration, and then we take the limit as t approaches infinity. And if you're starting to worry about, oh no, I haven't done limits in a while, don't worry, I'm gonna review them. Now, this is assuming a few things. Assuming that the integral from a to t of f of x dt exists for all t greater than or equal to a. In other words, assuming we can actually do the definite integral for a fixed upper limit of integration, and assuming this limit exists. And really, it's the second part we're going to worry about the most. What if we replace the infinity with a variable, do the definite integral, and then let the variable approach infinity? So replace the problem with a variable, do the integral, now take the limit. For the second type, where we have negative infinity as the lower limit, it's pretty much the exact same thing. We replace the problem, negative infinity, with the variable, t. Leave our upper limit alone, so we're calling it b. And we evaluate this integral, the integral from t to b of f of x dx, then take the limit as t approaches negative infinity, since that's what our original lower limit of integration was. And actually, these aren't strategies, these are really actually definitions. This is how we do these problems. Just like the first type, this one does have a couple of assumptions. This is assuming, excuse me, the integral from t to b of f of x dx exists for all t less than or equal to b, and assuming this limit exists. By the way, if the limit doesn't exist, then neither does the integral, and we will say that the integral diverges. So what do we do if we have an infinity on both ends? Your first instinct might be to just replace one of them with a letter and the other one with a different letter and do a quote-unquote double limit, which isn't impossible. Or maybe replace one with a t and the other one with negative t and just let t go to infinity. That could work, but I'm sure there are counterexamples to that. The trick to attacking an improper integral that has a lower and upper limit going to infinity, negative infinity, is to split it somewhere in the middle. Because remember, when you do an integral, you're basically calculating an area under a curve. So we'll say a to b f of x, and this area would be the integral of f of x dx from a to b. But if we were to stop in the middle somewhere at c, then intuitively the integral from a to b should equal the integral from a to c of f of x dx plus the integral from c to b of f of x dx, because we're just saying the whole area is the sum of the two smaller areas. And that's what's going to drive this third one. We're going to split this into two integrals, but where do we split it at? And the answer is any number between negative infinity and infinity. So we'll just call that number a. The integral from negative infinity to infinity is defined to be the integral from negative infinity to a, f of x dx. And remember, we've already defined how to do this up here, right here, plus the integral from a to infinity of f of x dx, provided both integrals exist. So it's standard problem-solving procedure. You take something you don't know how to do and turn it into something you do know how to do. In this case, we take this and turn it into two of these. And each of these we turn into an integral that we can do, followed by a limit. So this is going to be our strategy. If there's a single infinite limit of integration, replace it with a variable, complete the definite integral, and then take the limit as t approaches infinity or negative infinity accordingly. And if we're going from negative infinity to infinity, then we pick any number between negative infinity to infinity, split the integral there, and then work out both of those separately and combine the results if they exist. By the way, if you can pick any number at all, I usually pick a convenient number like 0.